Good evening, ladies and gentlemen. My name is Matthew Kerner. I'm a program manager. I work on Microsoft Azure, and I've been on the Azure team since 2009. It's a pleasure to be here. Thank you for joining us this evening. I know that it is late in the day, and we can see that you guys are the stalwarts who are really here for this information, so thank you for coming. Who's from Chicago? All right, watch out for those guys, because they're tough. I came to Chicago for the first time, most recently, a few years ago. Beautiful summer day. I went for a jog with my sister. She lived here at the time. We went to the beach. It was fantastic. I was wearing shorts and a t-shirt. And then we got on one of those boats that goes along the river, and you can see the buildings. And we were in the shade, and the wind started to blow. And I became extremely cold. And I ended up huddled under in the men's bathroom underneath the hand dryer, trying to stay warm. And I thought, these Chicago people are tough. So watch out for them. It's a pleasure to be here. Jeff, who's here, and I are going to talk about Azure Data Center and Network Infrastructure. And I think this is a pretty interesting talk because we're not going to be covering exactly how you're supposed to use Azure. We're going to be talking about sort of what's under the hood. And I think it's a pretty interesting topic because this is the thing that we live day to day. So we'll share a little bit of that. We can take questions at the end. I don't think this is going to take us the full 75 minutes. So hopefully we can also let you out early. When we talk about Azure, we talk about three things as differentiating Azure. The first is the notion that Azure is a hyperscale cloud. And there are really only three clouds in the world that are hyperscale. Microsoft runs one, Amazon runs one, and Google runs one. Now, you could argue perhaps in China, Ali runs one. That's perhaps a hyperscale cloud in China, but that's really it. And this is talking about the quantity of global infrastructure that's required and the capital that's required to build that infrastructure, and then the number of customers that are on board and the relationships with those customers. And so across a wide variety of dimensions, we talk about hyperscale, and Azure is one of those clouds. The next thing we talk about is hybrid. And Microsoft's legacy and heritage as an IT vendor is that we've got a tremendous installed base of Microsoft software on premises. And we want to make sure that that software works really well with our cloud. That's a strategic thing that's very important to us. And so there's a huge investment across the company, not only in hybrid capabilities of the cloud components, but also specifically hybrid workloads and capabilities, even in on-prem software that we build. And so that's sort of one of our sort of major strengths, I'd say, and a differentiating factor. And then the third is this notion of Microsoft Azure as an enterprise-grade service. Enterprise-grade with respect to the infrastructure and the quality of service it delivers, with the compliance certifications that it's got, with the sophistication of the relationship between Microsoft and your organizations that consume the services that we offer. And across all those dimensions, we strive to sort of meet that commitment of satisfying your enterprise's toughest requirements. Today, we're mostly going to focus on the hyperscale dimension because that's the thing that plays out the most in data centers and networks, although there are other pieces too. So we'll talk through that as we go. When we talk about hyperscale, I think it's just important to quantify that in some ways. We've got 90,000 new subscriptions a month on Azure. It's a tremendous growth rate. These are net new people who are coming and saying we want to use the service. They come in over the web or they're associated with an enterprise agreement. And they want to use the service, we've got to cater to them. So that's a tremendous ramp. We have about 500,000 active websites in Azure, and we have about 500,000 users of Azure Active Directory. So a tremendous scale there. And then SQL Azure is a tremendously large service as well and growing, and so that's just about 1.5 million databases. So these numbers are staggering. It takes a tremendous amount of effort to make sure that these services remain available and performant and secure, and so that's sort of what we are talking about. Let's talk about the data center, and sort of to work our way into the data center topic, I would back up a little bit and talk about our worldwide footprint. So in 2013, we had 11 regions, which is the same number that AWS has today. And then we kind of went on a tear in 2014, and we added 8 new regions. That brings us up to 19, which is more regions than AWS plus GCE combined today. And we are in the process of putting together our India regions. And so I can say at this time that we have 3 regions that we're planning in India. I can't say where they are or when we'll announce those, but we're hard at work on that. And you will see us continue to aggressively expand worldwide. The sentiment that we hear from customers and partners is that they really want their data to be local. They don't want to have to rely on public cloud footprint somewhere else. And so we're going to look at how we get into every market that really matters to our largest customers. And not just our largest customers, the customers that are giving us this feedback. So tremendous regional growth. And when we talk about regions, I think it's also really important for us to talk about the principles that underlie how we operate in those regions. And there are three models that we have today. The first is the public cloud. The public cloud is operated by Microsoft. The lion's share of the capacity that runs on Azure is in the public cloud. And we make a promise when it comes to the public cloud that the data that you put into a geography within Azure remains in that geography. And that's documented on our Trust Center. Now, of course, we're bound to comply with the local laws. And you can read about that on Microsoft.com/transparency. You can see the count of times that we've been requested by local law enforcement to turn over data in each of the markets where we operate. And we have a very specific, repeatable process to evaluate the validity of those requests and then to serve those requests if it's required. And all of that information is up there. Now, some customers cannot run in public Azure because of the things that I just mentioned. One segment that doesn't typically use public Azure is the public sector segments in the United States. And for that purpose, we've got Azure Government, which is a totally physically segregated cloud. It's got separate capacity, separate network. The operators who run that are cleared. There are a set of compliance certifications that are specifically designated to appeal to our public sector customers. And if you are a federal, state, local, or tribal customer or partner, you are eligible to participate in this cloud. And if you're interested in this, find me afterwards. We can hook you up with the right folks. And so this is available today. And it's actually the only government cloud in the United States that has true geographic redundancy. We've got two Azure government regions. If you look at AWS GovCloud, they've got a single region in Oregon. If that region were to go offline for any reason, well, then either your service is down or your service is running out of a non-secured, non-government only region. And so there's a big trade-off there that we think that we've got a leg up on. Now, Azure in China is another service that we operate. Actually, we don't operate it. It's operated by a partner in China called 21 Vianet. And they run the service there. They've got the necessary licenses and the ability to do business in China. They run the same technology that we run in the rest of the world, but they run it inside of the Great Firewall. So you can serve customers inside of China with great proximity, which you couldn't otherwise do. And we're actually the first multinational cloud to enter China. I personally spent about 3 years working on this project, and it was quite interesting to figure out how to take what Microsoft runs at hyperscale around the world and figure out how to package it up in such a way that a partner could run it in a market that's quite different from the markets that we operate in day to day. So that's a pretty interesting offering. And the nice thing about that is that it's the same APIs, the same resource model, the same set of sort of concepts that you'd use in the rest of the world. If you're an enterprise and you're doing business on Azure anywhere, you can take the same stuff and just deploy that stuff in China. And so this is sort of the backdrop to the data centers that we operate. And both at the data center level and at the level of our software and at the level of our operations, sort of the procedures and processes that we use, we go out of our way to make sure that we certify those things with all of the compliance certifications that you might expect. And these things fall into several categories. I find when I talk with people about compliance, they fall into one of two buckets. Either they know a lot about compliance, in which case they know much more than me, and I leave it to them and they understand exactly what all of this means. Or they look at this and they see a sea of logos and they don't really know what this means. And I think compliance can be boiled down to a couple of very basic things for those people who are not on the inside on compliance. The first thing is, in some cases, it is simply a requirement for our infrastructure to achieve a certain certification in order for your enterprise to trust your business to our infrastructure. And so in some cases, we have those certifications, and that means that we're eligible to do business with you. The second case is, there are a variety of organizations that stand behind these compliance requirements, and they define a set of controls that need to be in place for the infrastructure to meet the certification requirements. And we've gone and we've worked with auditors, independent auditors in each case, to show them the procedures and the technology that we use, and they attest that those procedures meet the control requirements that they've got. And so there's a notion of trust that's carried along with compliance, and you can look across and see the different organizations that gave us these certifications and say, okay, look, there's a third party out there that attests that Microsoft runs this service in a trustworthy way. The third thing is, you may need to get these compliance requirements in order for you to do business with your customers. And in that case, it can save you a tremendous amount of money for you to run on our infrastructure that has achieved these requirements, because then the only thing you need to do is get the certifications for the application. You don't have to worry about the infrastructure. You don't have to worry about the procedures used to operate the infrastructure. And this can save people millions of dollars for an application, because it really is a tremendously onerous and difficult process to go through and get these. And if anyone is looking at getting certification and they want to talk to us about the lessons that we learned in getting all of these and maintaining them year after year, I'd be happy to connect you up with the people who do that. We could have that conversation. I'll also just note the one on the upper right, ISO 27018, is kind of an interesting one. We're actually the first public cloud to meet data processing requirements for PII. This is an ISO standard that BSI put together. They don't actually certify you, but we sat with them and we walked through the procedures that we have in place, and they said, yeah, it looks like you actually meet this. So we kind of like that one, because Microsoft, in general, is making a tremendous effort to be at the front in terms of privacy guarantees. And this is one of these privacy guarantees, that we handle your personally identifiable information as a public cloud in a responsible way. We don't disclose it willy-nilly. We don't use it to sell it to co-marketing. You know, we control it. We tell you who the sub-processors are. We give you an option to opt out of our service if you don't like the things that we're doing with that data. So now, sort of the final step before we go talk about data centers is just to sort of frame up where the data center sits in terms of our regional hierarchy. We've talked about the different clouds, and we've talked about the notion of geography. It's a geopolitical boundary, and we keep your data within the geography, and that geopolitical boundary matches the requirements that we hear from the majority of our customers. Now, within geographies, we have regions, and regions are disaster-isolated units of capacity that run isolated software so that you can achieve DR-level isolation between them. And typically, regions are far apart enough that you have to worry about the network latency between regions, and it becomes prohibitive to use the standard techniques like synchronous replication that you might think to use in order to keep your data consistent across those regions. And so region is a very important thing for customer proximity. It's a very important thing for disaster isolation. And of course, the big concern there is latency. Within the scope of a region, we offer multiple fault domains. It used to be 2. As of last week, it's now possible to have 3 fault domains for your IaaS deployments using the new APIs that we announced with Azure Resource Manager. So you can run stateful applications across 3 fault domains and maintain quorum even if one of the fault domains fails. And so fault domains are isolated units of capacity within the scope of a region. There's less isolation than you would get across regions, but typically what we see is the failures that we encounter are confined to the scope of a fault domain. And these fault domains, of course, live within our data centers. We don't expose data centers directly, but data centers are very important when it comes to sort of the scaled infrastructure that we operate in order to support the model that I just talked about. Microsoft has been building and operating data centers for a very long time. And when we got started, we did it in a way that was sort of an industry standard way. And we would just, we used the sort of standard technology that was there at the time, and we operated the data centers, and we didn't think too much about it. And then as more and more of our business switched to a services orientation as opposed to a box product orientation, we had to start getting smart so we could operate these data centers at scale. Sort of the first big push was to run denser data centers. We said, look, let's run the data center hotter. We can pack more stuff in, and we can save some costs. And so density was this initial big focus. And then the insight was, well, if we're running the entire data center hotter, we're spending a bunch of money cooling that data center, and we don't have to be so inefficient. We can actually segment the data center and build some containment in. And so we built data centers following that, where we built these hot aisle containment units, which is basically a shield around 2 different aisles of servers. So there's a cold aisle and a hot aisle, and we push the cool air in from the cold side, and it comes out the hot side. And it ended up that we didn't have to cool the entire data center all at once. We could cool in a much more directed, pointed way, and it was more efficient. And you see these PUE numbers going down. PUE simply indicates the ratio of energy that has to go in to account for both IT power and cooling. So as you drive down PUE, the cost of cooling the data center drops down and it becomes more and more efficient. The goal, of course, is to get to 1 so that you're just putting in the energy that you need for IT power. You don't have to spend any extra money or power cooling the data center itself. Sort of extending this notion of containment, we went to an extreme with this notion of a modular data center. And in a modular data center, we take what's effectively a truck or a shipping container, and we pack a ton of servers in there, and there's almost no space at all for people. The data center was already a lights-out data center, so the operation of the data center was automated. Of course, somebody needs to be able to squeeze into a thin aisle to replace bad components in a server, but that's about the only space in the data center that exists other than the servers, the networking gear, and the cooling equipment. So these modular data centers take up a small footprint, they're quick to build, they're extremely cheap to cool, and so that's sort of I'd say a step function in the design of the data center that really drove down cost and really drove up efficiency. And what we've been doing since then is working on a sort of an integrated system combining software and hardware to totally automate every single aspect of the data center. And I think one of the big investments there has been on the networking side. Jeff is going to cover that, but I wanted to talk a little bit about the data center shell, let's say the building shell, the hardware that's in the data center, the cooling technology that's in the data center, and how we handle energy within the data center, as well as some of the general software capabilities of the data center. So that's where I'm going to spend the rest of my time. We are building tremendously large data centers today. And one of the designs that we're sort of currently working on has a data center that's about the size of a football field. And if our business is not successful and we can't sell capacity in the public cloud, we could repurpose these things as airplane hangars and bring 2 planes in, and they would fit inside of this building. And so it's a tremendously large unit that we're working on building right now in some of these hyperscale regions. Why would we do this? Well, it ends up that in some areas of the world, the capacity demands are so great that we just don't think we can keep up with the growth curve that we're on in terms of the physical hardware that we need to bring into the data center unless we have the ability to do it in tremendously large tranches. And so that's where the design for this extremely large data center came in. It's just an enormously large place. And in December, I went and I toured. And one of the things that struck me about a site where we're building one of these in Washington is that there was a lot of engineering that had to go into building the parking lot. And it was sort of the first thing that they spent building, because the number of cars that have to go on site every single day for the people working on the site is mind-blowing. I mean, it looks like you're approaching an extremely large mall, except everybody who chooses to go shop there is driving a pickup truck or some other kind of commercial vehicle. And there are people building buildings, there are electricians, there are plumbers, there are mechanical people. It's really an unbelievable thing when you go see just the scale of the parking lot at the construction site to then go build one of these data centers. So it's a tremendously large investment in physical infrastructure in order to house servers at the scale that we need to in order to satisfy the demand from customers. And that physical infrastructure has these downstream effects on the power infrastructure that needs to be brought into the area, on the roads that need to connect the construction site up with the places where the workers live, on the parking lots, et cetera, and the facilities that need to be there just for construction. So the scale is amazing. And as soon as you think about building a building at that scale, you really have to think about how to make that building efficient. Of course, making the building more efficient saves us operating costs, but it's also a responsible thing to do. We all consume a tremendous amount of services, and every single one of those services is consuming energy somewhere, and we're generating emissions from those things. And so when we think about our carbon footprints, one dimension of that is thinking about the footprint for the IT services that we consume. And so it's important to us as a hyperscale cloud provider to responsibly build data centers. And the insight here is that when you're running at scale, you can sample a tremendously large number of devices, and you can then learn about how devices fail. And the observation is the standard operating temperature that you might expect for a device certainly prevents the device from failing more frequently, but it's a tighter set of parameters than you actually need. It's possible to run devices outside of the standard thin tolerance for periods of time, as long as you bring them back into that tolerance some of the time. And the work that some people did, whose names are listed here on the right-hand side underneath the table, was to sort of quantify how big the window could be where we allow things to exit the standard band. And what that lets us do is we can back off on the cooling and on the humidity inside of the data center during the hottest hours of the day or the most humid hours of the day, when it's the most demanding to cool the data center. So we let the data center run hot, and then we bring it back inside the tolerance at the hours when it's cheaper and less environmentally impactful to cool the data center. And so that's an insight that you can get when you run at scale, and that you continue to calibrate when you're running at scale. Because we're continuously buying new generations of hardware, so the parameters that we identify might be good at a certain point in time, but over the course of a year, the parameters might vary. So we need to continue to sample and understand that. The other thing that we can do, and we can't do it in every single region, but in many regions, we can run the data center using what's called adiabatic cooling. And Microsoft was a pioneer in this, actually. And so the way that you do that is you effectively run the data center as a big chicken coop. When you want to cool the data center, you pull in outside air, you push it through the data center, and then it comes out the other side hot. You never spend any time cooling the air down. All you spend the time and energy doing is moving the air. And it's much more efficient to move air than it is to cool air. We don't need a chiller. We don't need to run these expensive, power-hungry conditioning devices. And so this works, again, in some regions, and in other regions it only works some of the time, not all of the time. But any time we can just use ambient air to cool, we'll do so, and we'll do so using both of these techniques together. And so it ends up being a really efficient way of operating the data center when you're running at scale. So that's cooling. The next thing I wanted to talk about is power. If you think about a traditional powertrain, and you think about the infrastructure required to support that powertrain, you've got to back way up from the data center. So there's typically some extraction that goes on, whether it's coal or oil, perhaps it's nuclear, perhaps it's hydroelectric, and certainly we seek out regions in the world where we can get cleaner power. But typically, there's a fossil fuel source involved in a fair amount of the power that we would consume. And then we generate electrical power out of that fossil fuel, which is a lossy process. And then we push the power through many stages of the powertrain, starting with substations at the power company, and then across a whole bunch of different lines, and then more substations locally. Finally, it makes its way into the data center. It goes through several different stages of transformation, and then it goes into the rack, and then it powers the server. And by the time you get to the server, from the place where the power originated with the extraction, you've spent a tremendous amount of energy converting, first of all, fossil fuels into electricity, and then second of all, you've lost a bunch of the electricity that you initially had, because every single stage here is lossy. And it's very difficult for us as the cloud provider to optimize the whole train. We can go back to the power company and we can look for places where we can get green power, perhaps, but still they're going to run their substations the way that they choose, and they're going to have the transmission lines that they choose to build. So we only have limited ability there to change things. So we're doing this very interesting pilot. There's a wastewater treatment plant, and it generates methane gas. And obviously the methane gas is a problem because it goes up into the atmosphere and it destroys the ozone layer. So you wouldn't want that methane gas, but it's a byproduct of this wastewater treatment. And we said, look, we'll take the methane gas, we'll pipe it into the data center, and we'll feed it to a fuel cell in the rack, and we'll generate power right there. And so we've taken away the methane gas that was itself a problem, and then we've gotten rid of this dependency on the entire powertrain, this lossy powertrain, and we go straight from sort of this byproduct, which nobody wants, into energy that we can use right there at the very place where we consume it. Again, it's not like there are wastewater treatment plants next to every single data center that we build. Certainly we would seek that out, and we would use it when we can. But this kind of thing is the kind of thing, there's an energy strategy team within Microsoft that works on this globally, and this is the kind of thing that we love to do where we can. And a lot of this is really original work that nobody else is doing. So we're working on innovating on the energy side. It's cheaper for us, it's better for the environment. And certainly the wastewater treatment people love us because we take away a problem that they generate. So we've talked about the building, we've talked about cooling, we've talked about energy. Let's talk about hardware. Several years ago, up until several years ago, Microsoft purchased servers from the usual suspects, and then we operated those servers in our service. And the observation that we had was that since we have quite a bit of control over the data center environment, and since we're buying at scale, we can do some things to optimize the servers that we buy. And so Microsoft began the process of building out a server design team, which we've now got at scale, and we design the hardware that we run in the cloud. Not only that, we've made these designs available to members of Open Compute. So if anybody would like to build a Microsoft Cloud server, they can take the reference design and then work with the manufacturers of their choice to get that thing manufactured and shipped to them, and then they can run it. And these servers are flexible in the sense that we use them to run Azure, we use them to run Office 365, any of the services that we run, we're using common sort of fungible SKUs, and we make sure that those server SKUs meet the requirements of each of these different workloads. In some cases, we have to make some compromises, and I spend a fair bit of my time working with first parties within Microsoft to understand what the right choices are on how we land on fungible infrastructure so that when one group's demand isn't what we anticipated that it would be, we can reuse anything that we have in the supply chain for somebody else who may need additional capacity at that point in time. Now, on top of this hardware, we're doing some interesting things in terms of cloud leadership. The largest VM size available from any cloud provider anywhere, any sort of hyperscale cloud, is this G-series VM, which internally stands for Godzilla. And it's just a tremendously powerful VM size, which some customers really need for certain workloads. They need a memory-intensive and I/O-intensive machine. And so we make that available, sitting on top of this commodity infrastructure that we've designed. The other thing that we announced, I believe it was last week, maybe the week before, is Azure Premium Storage, which is an SSD-backed storage offering to improve IOPS and reduce latency for workloads running on compute in Azure. And nowadays, if you create the right VM size and you add the maximum number of premium storage disks to that, you'll get 50,000 IOPS, which is the most IOPS in any public cloud provider in a single VM on top of durable storage. And so we are leveraging this investment in hardware inside of the data center to offer differentiated capabilities to customers running on the public cloud. Now, I mentioned before that sort of the current investment that we're making is to integrate hardware and software in the data center in a novel way. And so I just wanted to talk through some scenarios that software manages automatically in our data centers. And there's a tremendous amount of investment on the team in these areas, including the stuff that I'll mention, and then other areas that are sort of adjacent that I won't talk about. The first is when you deploy compute within a region, we automatically allocate that compute across fault domains. Think of fault domains as mapping to a physical rack. There are single points of failure in the rack, like a top-of-rack switch, like a power supply within the rack. If either of those things were to fail, the entire rack would fail. And so the intent is that we now protect your service and make it highly available on top of this infrastructure. When you update your service, we have this notion of update domains. So we update one portion of the service at a time and then move on to the next portion of the service. You have fine-grained control over how that looks. This translates for us into a set of allocation constraints because instances in different update domains can never land on the same server. Instances in fault domains can never land within the same rack. So we've got this pool of capacity. Every single time a new deployment comes along, it's got a set of update domain and fault domain constraints. We match those things up so we can do the right allocation. And then at runtime, as we're performing disruptive operations against hosts or VMs, we make sure that we respect those things. In the event that hardware fails, we automatically detect that, and then we automatically service heal. This requires us to run with enough spare capacity such that the failure distribution that we see can be handled by that spare capacity. If we run with too much spare capacity, then it becomes difficult to offer competitive pricing to you because we've got to cover the cost of the infrastructure that we purchase. So one of the things that we need to do under the hood is very tightly ride this capacity curve so that there's effectively infinite capacity for customers. We're always maintaining the small buffer that we need in order to maintain availability in the presence of standard failures. And no customer should ever need to know how close we are to the capacity curve. And so that's a pretty interesting thing, and we've got a ton of investment there in terms of modeling and machine learning and predictions to understand how we manage our supply chain in the most effective way. This is one of these things that, at scale, there's a huge payoff in optimizing this area, and so there are a tremendously large number of talented people working on the supply chain optimization so that we can enable this without driving the costs up. Inside of a region, when you write to Azure Storage or Azure DB, we synchronously create 3 replicas of that data before we acknowledge the write. All of these services run on commodity hardware with just standard disks in the nodes, and then we have software-defined storage that sits on top of that manages the fault domains and update domains and availability of those replicas, not just at the time that we write it, but continuously scrubbing that data to make sure that it's not corrupt. In the event that servers fail, we have to re-replicate data. We have to deal with the fact that hard disks fail, and on some of these nodes, we've got dozens of hard disks, all being managed on a single node, so we've got to figure out sort of the right thresholds for when we go replace a disk and potentially disrupt the performance of that node while keeping enough copies of customer data such that it's always available and it's always durable. So there's a tremendous amount of investment there. We also give you the option to replicate your data asynchronously across regions. Again, I mentioned regions are far enough apart that synchronous replication is typically prohibitive for customer-facing workloads, and so this will be async. And it's the same technology on either side. We use Azure Storage or Azure DB to replicate locally redundant copies, as well as having locally redundant copies on the other side. Now, in the rare event that a region fails, we have traffic management, which enables you to configure policies to automatically redirect your customers to a secondary region. We've never had a natural disaster take a region out permanently. We certainly have had some regional blips. And so the goal is that you're able to deploy on Azure, you're able to take advantage of the software stack to achieve a level of availability that would be very difficult to achieve if you're building the technology yourself. So that takes us, I think, to the end of Data Center. And we're going to switch over to networking, so I'm going to hand over to Jeff.
Thank you, Matt.
Sure.
All right, good afternoon. My name is Jeff Cohen, and Matt is my partner today. First thing I want to say is it's Cinco de Mayo. It's 5 o'clock. What are we doing in this room? A little more excitement. Today, I'll go through the presentation, and I'll make it interactive, meaning that feel free to ask what I'm actually talking about. At the same time, we'll hold to the end for real questions so we can answer questions between Matt and myself. But you'll see, I made it interactive. How many people in this room know what a hyperscale network looks like? Yeah, Matt does. I see the guys over in GE do, because they're constantly yelling at me. Hypergrowth. So Matt touched on this earlier, but hypergrowth means that these are things that are occurring at a rate that even if I wanted to plan for it, I couldn't. So think about 5.1 trillion transactions occurring on our storage, or 50 trillion objects in storage. It really drives what we call east-west traffic, hopping between data centers or between racks. And just thinking about that and trying to place yourself in a mode that says, I'm going to build a network to support this, but the numbers are growing so rapidly. The 5.1 trillion is 3x what it was last year. To give you an idea of just how rapid the growth is. 425 million active directory users. These are people who have Active Directory either for their business or they're running on another service, and they're calling in Azure. So think about traffic going in and out of Azure at a high rate. And in addition, 450,000 active websites. A lot of I/O, a lot of traffic going in and out to the internet. And how do you handle this? And what's the scale dimensions to do so? As I mentioned, hypergrowth drives hyperscale. Hyperscale drives hypergrowth. And in this case, what I'm trying to show is that we dragged our core network out to 85 internet exchanges. We're connected to over 1,700 networks 4,400 times, meaning that sometimes you'll connect to a network in multiple locations. We have 1.4 million miles of fiber that is inside of our data centers. And we could wrap the earth 4 times just with the North American fiber. It's an enormous amount of capacity. And as you probably heard throughout the day, Microsoft has spent about $15 billion on its cloud services. So it's not an inexpensive investment. It really is a challenge to try to keep up with demand, which is a good thing, but mentally, you can outplan yourself, and you'll never get up to a place where you're actually filling up your capacity in a way that's effective. So I'm going to walk you through some ways that we go through it and how we think about it. So the first one is, where do I place the data centers? You'd seem to think it'd be obvious. You just place it where a customer is. But sometimes customers actually are hosting a service for other customers. So the obvious location may not be the one that just falls in your brain. Like, because I live in Seattle, using the data center closest to me is probably irrelevant if my customers are in China. So you should be thinking about, how do I get to the service that's closest to my customers? And what I try to overlap on this particular slide is internet population with the deep sea fiber cables. Because in my mind, that's where I have to think about hosting a service so I get closer to users and I can reduce the latency as best as possible. And on top of it, as Matt mentioned earlier, Azure has 19 regions. And you can see the regions now overlaying on top of the infrastructure. And this is how we try to pull it together to say, well, I can actually offer a service that's horizontal, that's distributed, that's closest to users to get the best performance, and at the same time, grow and scale the business. One other thing to mention is that we pair our regions together. So as Matt was talking about the geosynchronization of content, regions are paired. Doesn't mean all content gets copied to every region, but it does mean that you have the ability to offer that. You like my slides so far? Okay, I worked on them. This is a, everybody's so quiet. There we go. Okay, so this is an overview, high-level overview of what the global network looks like. On the left-hand side, what you see is just servers and racks and what we'll call top-of-racks and switches. And then the next column over are what I'll call software-defined solutions. Now, if you're in a big iron data center, you're thinking, well, I actually have something that does firewalling or DDoS protection, or I bought somebody's hardware to do load balancing. But in my world, as I go through this a little deeper, you'll see that I don't have the luxury of pre-planning. I have to make things ubiquitous and move very quickly to handle the scale and velocity. The next column I'm showing you is two of our backbones. We have multiple backbones. I'm showing two. One of them is what we call the core backbone. That's connectivity to the internet. 8075 is our AS. That's how we reach out to customers and partners globally. And then the second one I'm showing here is the inner data center fabric. This is the ability for me to actually get a variance in quality of service, but a much higher throughput for traffic to copy and replicate content between regions or between data centers. So I'm just showing you two of them, but it's important to realize that they all mesh over top of each other. They connect to the metro optical networks, long-haul networks, and from there we drag it out to edge locations around the world. Some of those edge locations are sitting in internet exchanges. Some of them are actually sitting in the telco, and we have a mix of them. And between all of that's how we reach out and make our services scale. In the edge locations, you'll notice a new service from Azure. It's called Azure DNS. So it was just announced today. And they set out at regions that are closest to customers. They give you a really good feel for this distributed DNS service as well as good performance back. So if you're someone like Bing or Google and you have a website, you need to get a fast response back to actually get a page load time down. It's a great way to offer that by putting content into the edges. So here's part of my interactive. I worked on these, but get your mind around it. Okay, you have a data center. The data center needs to support thousands of workloads. But at the same time, each of these workloads are unique. They have different bandwidth requirements, latency requirements, and security requirements. How would you scale your data center network to do so? And what I thought I'd walk you through is how we used to do it, and then how we do it today. So the way we used to do it is we built out a very flat network that was hierarchical, tiered, and every time I had a new workload, I'd sit down and say, well, I got to get my traffic engineers to come in and design and plan the hardware that's going to go in there. And that hardware would have a certain set of firmware They were intelligent pieces of hardware. And I'd lay that out, and I'd build my infrastructure. The problem is that if I have a growing agile infrastructure, sometimes this capacity that I built out would get locked into this layer 2 domain and never actually flow up. So I'd have some pockets that were very light in connectivity and some that were overutilized. And so you trap your capacity all throughout your network. We moved, as we're going through this, to say, well, how do we scale this out and give us the ability to grow this at a rate that's more complementary to a cloud business? And we came up with something that a lot of people have snapped to. It's the CLOS network. It's a mesh network, so you move away from this tree design. And in this CLOS network, you come back and say, we could actually run our services in software on commodity hardware instead of buying very expensive hardware that are single-use, very focused devices. So getting this flat network that's mesh-oriented enables you to get much more flexible. Most important thing is that I'm reducing the service engineers I have. I don't have people going out and trying to flash devices or rewire the network to handle a new workload. Instead, the workloads can come at me as rapidly as they want, and as they do, this new mesh network enables me to just push out new software and redesign a network on the fly as I need to. So just a different concept. Next question. And some of you are itching to answer this, but how do you support an unlimited number of customer-defined networks into your cloud? Because think about it, I don't have this opportunity now to move switches around and routers around. I can't rewire the network in just certain areas to handle some customers, not other customers. The workload is going to come at me constantly. How do I do this? And it's a super high demand and a super high rate. So how many people know what software-defined networking is? Okay. So I won't go super deep, but in software-defined networking, the concept is that you take the proprietary hardware that had this flashed software on there, and you separate it out so that you have multiple layers. And one layer is an API layer that you can actually get to, we call it the management layer. You have controllers that are software that sit in the middle, and your host box itself, the actual host server, and you run software across all these 3 layers. At the top, it's the API, the management, the way you'd actually reach in and say, please make a change, is the request from the customer. The middle layer, this controller, is really about defining policy. So you say, I'm going to define the policy in the middle layer, and then the bottom layer actually does the action on the policy. I'll go a little deeper so you can get a feel. So in this example, what I'm showing you is, say I want to play an ACL, something pretty common, and I take that ACL, you see at the top there's a person, and that person talks to Azure. They used to be able to talk to it through the Azure front end. This week at Build, you've heard about the Azure Resource Management solution. So I'm showing you the resource provider side. But the person makes the call in. They make a request into one of these controllers that happen to be a software-based solution that's distributed. And then the controller passes that request of policy down to the host, and the host actually does all the hard work. I'll go a little deeper. So here's the host. So just that circle that I had around one of the VM/host is now exploded for you. At the top, you see the Azure front end. I've shown you a couple different controllers. One of them could be your ACL management that I showed on the previous slide. But you could also have things like a virtual network or your load balancer. And they call into the host, and the host has these little tables. And the tables enable them to very rapidly make a decision. It says, I know this information. I could either choose to accept it or not accept it. If I accept it, I'll follow the policy. If I don't, I'll deny the policy. And you get all these little policy things that are running around that are part of what we call the virtual filtering platform. And that sits on the vSwitch that's inside of the Hyper-V. Okay, so think of all the processing work that's happening. Some of it's happening at the controller layer, some of it's happening on the host. But this combination of everything is what enables you to get this very rapid, dynamic, agile ecosystem that can handle billions of packets and grow and scale and change as your demands change. I'm going to walk you through a couple examples. So that was the theoretical. Now I'll walk you through a couple. So we have a software load balancer in Azure. We use the software load balancer to actually take all requests that come in and actually load balance it across different hosts. And the software load balancer really has two inputs. One of them is you as the user says, I'd like to have 5 tuple, or I'd like to have a sticky session, and you program that on the left-hand side. You make a request. And we have a service called the SLB manager. The manager is a controller, and the controller goes out and says, okay, I'm going to tell all the devices, which happens to be every host, follow this rule. On the right-hand side, you actually see the data plane. This is user comes in, hits your website. The website says, great, comes in and hits SLB, and the LB says, I know where to parse this content out, and it sends it to the right host. So a combination of both is what gives you this ability to have a software-defined load balancer as part of your ecosystem. So now I don't buy proprietary hardware to do load balancing. I buy commodity hardware, commodity servers, commodity switches, and I do all the programming myself. So if I need to make a change to this load balancer, I could do so. So an example of a change was about 3 years ago, we said, boy, we'd like to support UDP traffic instead of TCP traffic. We made that change, and we implemented it and deployed it. Someone else said, I need to have sticky sessions for media. That is, someone comes in, I want to go to the same server all the time. Great, we made the software, and we rolled it out. I'm not relying on somebody else to be in the way for me to get my agile features. I can make these feature changes myself. At the same time, I get an unlimited scale, because if it's not going fast enough for me, I can just buy bigger hardware, put more boxes out there, and distribute my code. Next one is kind of interesting, which is you have a network already in your business. In fact, some businesses have multiple networks. They're virtual networks. You may have the HR system and the finance system running right next to each other, but HR can't talk to finance, and finance can't talk to HR. In this picture, what I'm showing you is that you could have multiple enterprises, Enterprise A, which is orange, and Enterprise B, which is in the pink, and you can run them both up in the cloud in Azure, and they're segregated. They don't talk to each other, and one business's network is completely segregated from somebody else's business network. The line that you see on the far right-hand side, that purple line that says the orange and the pink can talk to each other, that orange and pink means you can go out some public IP and come back in. But the two networks do not talk to each other. They're segregated. It's your own business up in the cloud. Again, this is done through programming a controller, the controller being the VNet controller, virtual network controller. And on the host, we have this table that says, I know the IPs that are your customer IPs, we call them CAs, and the physical addresses that we know are there, which we call the PAs, and it does the CA-PA mapping on the host in real time, so it knows how to segregate what one customer is from another. We're now offering services called network appliances. A network appliance is where you could take something that you know and love, you use in your business today, and you can bring that appliance up into Azure along with your virtual network and run this in your virtual network. It could be a firewall, it could be a proxy, a gateway, intrusion detection system. It could be something you wrote yourself or pulled off the internet last night and hosted it. But you could take that and stick it inside your virtual network. That's what the blue boundary is. And you could take something that's already available off of the marketplace, or you can take your own, and you run it in that place where it shows you the little block of the red block with the lock on there. And so now you can say, well, I would like to direct traffic between my subnets. That's what the different stacks are there. So the finance department, if it's going to go out the internet, I could track all traffic that goes out the internet. Or if I want to take traffic that's going to go back to my premise, I can direct it and force traffic back to my on-premise. And while the appliances themselves aren't really what I'll call SDN, they leverage the SDN technology. They leverage technologies that we're able to build by creating more controllers inside of Azure and letting the host look at these tables and make those decisions as to where it should send the content or deny the content. This week, you probably heard a lot about ExpressRoute. It's our premier service to take somebody's MPLS network that may be on your campus and bring that up into the cloud and connect it to our backbone. But you could also take IPsec tunnels, that's on the far left-hand side, or you can take the center and right ones, which are ExpressRoute. But those services, again, while not SDN per se, they leverage SDN technologies to create tunnels, to be able to create security, to be able to give you the ability to route your traffic to your on-premise or from your on-premise back up into the cloud. And those capabilities are all what we consider software-defined networking. And the really cool thing is that everything that you do on your premise, you can do in the cloud exactly the same way. So it's not that you're locked one way or the other. You can actually grow your business. Okay. So we've got these concepts in our brain. We talked about the ability to take the network design that used to be this tiered network and make it a mesh network. We talked about the ability of taking your private network, your virtual network that you have on campus, and move that to the cloud. I mentioned a little bit about the appliances and connectivity back. But what happens if we took this concept one step farther? What happens if we said, you know what, I want to take the whole WAN and make the WAN itself an SDN device? So this is one of the things that we do that's less obvious, but we took our WAN and converted it over to a software WAN. It's expensive, slow routers that you buy from some very, very large companies. We commoditize with commodity hardware, and enables us to change the way that we actually flow traffic for our business. And if you're interested in this, you just have to do a Bing search on Microsoft space SWAN, software WAN, and you'll find some papers that we published a couple of years ago. But the interesting thing is, if you look on the top right-hand side, the very top picture, this is what most people's network looks like across the WAN. You have some peaky traffic, and the traffic comes back down and goes back up. And so if you're trying to decide, boy, I want to buy a certain quantity of pipe between my data centers or my region, it's very hard. You have to go for the biggest one because you don't want to drop packets on the floor. With the software WAN, what we're able to do is say, let's look at the traffic that's background traffic. That's the blue. And let's look at the foreground traffic. The foreground traffic would be things that require a high quality of service. The background traffic are things that don't require high quality of service, like replication between regions or backup, things that you just don't have to rely on a certain time series to get content out. And if you can separate those two and then control the blue traffic so that it fits into a smaller pipe, utilizing more of the pipe, you say, wow, I've actually reduced my cost of business dramatically. And if I need to increase it, I just change the software and say, you know what, I'm going to have a bigger flow table. So just this mental view of something that you couldn't do before, now you can harness that connectivity and actually drive it. The cool thing is that what I just explained to you is a set of APIs. So if I wanted to take an application like Link, which has video and voice, and say, Link, I'd like you to go over and make this connection with high quality of service, it can make a request to the ecosystem, and the WAN can come back and say, for that particular service, I'll enable this. Someone else has a backup service or a Microsoft update, we just jammed it into the lower quality of service. Just get your head around it. The bottom right picture is about greedy allocation. Greedy allocation is not your IT director saying, I'm taking your money, though I know some in the audience would like that. Greedy allocation is that if I'm only focused on one network and one data center, I'll allocate whatever I think I can get, and I'll send the traffic any way I think I can go, and I'll do it the cheapest way I believe that data center needs to send traffic out. But if you can optimize it, which is the bottom right-hand picture, and say, you know what, I know A and B are closer. I know how much capacity is between A and B. I know I don't need to send traffic across the world and back to get between two data centers. I'll decide to actually burst my traffic on certain pipes just for the quantity and for the time period that I need to do so. Okay, and again, you get to control this because you own the software, you own the controller, and you can have your APIs and your applications talking to it to actually make the best decision. And on the left-hand side, what I was trying to show you is the example of the SWAN network. So again, no new concepts here. The concept is there's a controller. You have these agents that are working on the host. They can sense traffic load. They can sense demand. And they can make decisions and say, you know what, I think I'm going to send this information back up to the controller and let the controller make an ultimate decision. The coolest thing about this is not what you see on the picture. The coolest thing is that you actually can model this. So if I know I have a workload that's coming in, I can model this, I can actually deploy the modeling agent, and then make the change. So I don't have to make the change on the fly while customers are expecting some experience from me. I model it, I make sure it works, I push it out. Now I have something I know it's going to work. So it'll give you an idea of a software-defined network WAN. All right, coming to the end. So all this is great, but if you can't monitor it, you can't manage it, then it's probably worthless. I thought I'd expose just a little bit about how we do some of the stuff at Microsoft. How do you think we manage 19 different regions or millions of devices? And I say millions of devices because there's a physical NIC in each machine, there's TORs, tops of racks, there's switches, routers. How do you think we manage it? It'd be almost near impossible. And so the first thing that I'd show you is that we actually look at the SLA. And the SLA is really about performance SLA, not about the SLA like if I miss it, I have to pay somebody money for the SLA. And I try to figure out, continuously measuring latency and traffic patterns across the network. And so what you'll see on the bottom left-hand side, I'm sorry the picture's small, is this constant analysis between host to host, host to the top of the rack, rack to rack, rack to the router, router to another router, and back down again. And imagine this thing pinging constantly. And what it's pulling back is essentially these little race tests that are then aggregated and shown on a picture where you can alarm and alert yourself when you say, wow, something seems like it's coming out of SLA, either between two racks, between two hosts, or between two data centers. And with it, you can then actually address those problems automatically instead of creating tickets and having engineers touch it. You know what the problem is, you've seen the patterns, and you may have to go back and tell your SWAN to reallocate software, to go over and reallocate its bandwidth. So this is a continuous closed-loop process, but it really gets you in a way that you think about your business end-to-end instead of thinking about just one network and one controller in a data center. The right-hand side is a slice of a tool that we use to give visualization to both predictive and past issues that occur inside of our ecosystem. So what you'll see, and unfortunately I didn't put the labels on there very well, but the rows represent data centers. The columns represent services. Quickly you can say, wow, I have a service in a data center that's going bad. Okay? And then with that, you can double click on that and you can drilling in all the way down to the NIC to find out if the NIC is falling over, or if it's the controller, or if it happens to be a user problem, or maybe it's something coming in from the internet and you want to understand, say, from Gomez or Keynote, you could see the same thing on the same screen. And while this is collecting this information, it's collecting it real time, so you can go back and play this back for a week or a month or a year and find out, did a network change? Did a pattern change? Was it happening only when a deployment occurs? Does it happen only when somebody decides to build out a new ecosystem? You have all these controls to run your business. And then lastly, it's great to have all this data, but you want your control plane and you want your monitoring plane to be able to report out if there's problems proactively. And so you can take action on those problems. And some of that is human intervention, and most of it is software intervention. So, lots of people are using Azure. Lots of people are using our cloud. 85% of the Fortune 500 bet some of their business on us. And hopefully it gives you a little better feel for how we scale both in the data center side as well as the network side to handle the lots of changes that we have in our business. So with that, I'll invite Matt up and see if we can answer any questions. I know it's late on a Cinco de Mayo day. I promise Matt will not dance for you. Okay, I won't promise much of his dancing. But thank you. Gentleman in the center, yes. You look like you're familiar.
The SDN environment, is that proprietary to Microsoft, or are you leveraging other technologies that you use?
So the question was, is the SDN technologies proprietary to Microsoft, or do we use open source solutions? I'd say all of the above. We're open to looking at open source solutions, and we're also looking at our own solutions. It just depends on where you can get the agility. So if I could pick up something and get it into the business fairly quickly, but I know I can modify it at my own rate, then we'll do that.
One of the pieces of technology that we use in our SDN solution is a framework that sits on top of Azure Storage called Rtable, which is now open source, which gives you a globally consistent view of Azure tables with distributed components running in each region. They can all write. It just takes care of ordering, et cetera. So some of the things that we do are Microsoft things that we then open source. Not just in the networking space, but that's a networking example.
Did you guys like the demos? Yeah. Just checking.
How do you guys manage public IPs for?
How do we manage public IPs?
Yeah.
So we have a IPAM system that is not something to scream about. It's actually, when you get a large company like Microsoft, you have different territories that own its IP set. And so in areas where it's much more publicly available, meaning that one group owns it, then it could sit in an IPAM system that everybody can have access to. And areas where it's locked away because a business wants to hold on to their IPs, like any other company, it's locked away, and you have those challenges in trying to pull ranges out from them. It's not a good answer.
On your layer 2 overlay, and then the monitoring piece, you guys look at it, inside of that overlay at a host-to-host kind of traffic monitoring. So how do you describe that at all? How you do that?
Sure. So Lance asked, let me see if I can repeat it. At the layer 2 level, where I showed the visualization on monitoring, how do people actually track that or look at that? For most of the time, it's actually creating alerts automatically. The system will look at something that's out of desired state and say, hey, the state's not where I expect it to be. Go troubleshoot this. Otherwise, the system's going to try to constantly self-correct and meet the desired state. We try to optimize for automation instead of optimizing for human touch. And I can spend more time with you, much more detail.
There are actually 3 sources of problems that we generally respond to. The worst case is when customers call us saying, I'm having this problem, if it's something that we hadn't detected. So we have these customer-reported incidents. So of course, we jump on those. Sometimes, and the challenge there is distinguishing between those things that are customer-specific because they've done something that impacts their own application and those things that are infrastructure problems. So we have customer-reported incidents, CRIs. And then the second source of problems is called live-site incidents, or LSIs. And with LSIs, I would actually break it into 2 different classes, which gives us the 3. The first are those things that we detect because there's a specific point in code where we alert because we hit a path that we didn't expect to hit. And then the second case is we've got a set of monitoring that we have. It could be Gomez or Keynote, external outside-in monitoring. It could be looking at quaz data and alerting when we see things outside of a threshold. Or it could be our own synthetic transactions that we're running either locally or from another place in Azure to see that those things are succeeding most of the time. So there's a variety of different sources that can all generate these alerts. The alerts flow into one of several different severity levels. And then we've got some classification, escalation, and notification rules about each severity level. Much of the notification and the handling of each of these things is automated. In some cases, we just auto-mitigate. In other cases, people get called. And that would typically done on a component-by-component basis where there's an on-call for the component team. And so the devs who write the code are on call. They go and they are responsible for mitigating that incident. And then they can get access to a whole bunch of historical monitoring data, some of which we might have alerted on if something was strange. But most of the time, it's used by people to look back and see when things change, what changed. They can drill down or they can look at details. And as they resolve things, then there's a bunch of machinery that they can use to quickly resolve. So for example, we minimize the number of people who have standing access to the system. So if somebody needs to log in to deal with stuff, they've got sort of like this two-factor authentication piece, and they get some just-in-time privileges that are scoped and that last for the duration of time that we have that incident. They'll go and they'll work on resolving that incident. There are a variety of troubleshooting and diagnosis tools that are available, these sort of prepackaged workflows that other people have come up with over time, so they can use those. Sometimes there are component-specific tools like the network monitoring stuff that you included some screenshots of, and it really varies by component. And then, of course, we've got sort of all of the tracking of the different incidents that occurred, so we can look back. And actually, there's a weekly review with executives in Cloud and Enterprise where we will look back at severe incidents from the prior week, where there's a root cause analysis, and we kind of talk about what the root cause was, what were the diagnosis and mitigation gaps, how could we reduce time to mitigate in the future, are there classes of problems that we can address through repair actions, when do those repair actions get scheduled, is it hot fix, next release, next planning cycle. So there's kind of this structured process for dealing with those. And then there's actually a monthly review on service health with an even larger room where every single component is looking at a variety of KPIs around security, availability, performance, disaster readiness, et cetera, where they're looking at the overall trends and metrics, and we kind of have a conversation in the room about whether we're headed in the right direction or not and what changes we need to make. Sometimes we do some special topics, and we'll also spend a bunch of time looking at specific first parties to try to understand what their experience is like as kind of a canary for the broader customer base. And then we've also got some programs where particular customers decide they want to talk to us more closely, and we can work with them to look at their metrics on a regular basis, including on special topics like, for example, VM availability is one that we spend a lot of time on. So we'll look at VM outages and try to understand where those outages came from, and then come up with the overall set of investments we need to make to drive those things down over time in frequency and duration and severity. Yeah.
You said you're in like 19 regions now?
Yes.
Did you say that the pace of expansion into new regions is accelerating or slowing or kind of stable?
Is the pace of expansion into new regions accelerating or slowing? I'd say we are more aggressive now than we ever were, and we are also pushing the envelope for internally in terms of what we can do. So one initiative we have going on is something we call Go Local, and the goal there is to build as small a footprint as possible for the combination of Azure, Office 365, Dynamics CRM, the set of services that manage customer data where we would want to enter a region together, because those things sort of run together and talk to each other, and we want customers to be able to stitch together different pieces to solve problems for their business. The smaller we can make the footprint, the more regions we can go into that are sort of economically viable for us. So there's a big effort to drive down that minimum footprint so we can expand into regions that otherwise might not have been feasible. There's also a big effort to leverage the work we did on Azure Government and Azure in China so that we can reuse that operating model in markets where just expanding the public cloud maybe doesn't make sense. And so we tend to try to keep this stuff very tight and not talk too much about where those places are. But we think, based on the work that we did for the existing national clouds, that we've got kind of an operational capability that's differentiated, and that over time will enable us to enter markets in a way that is very friendly to local restrictions on how things operate, where, for example, Microsoft personnel having standing access to customer data would be a problem.
So these would be in data centers that aren't the football size?
I see. So the question is, what about, we showed an example of a football field-sized data center. Is that the data center we stamp out everywhere, and how does that intersect with this regional expansion? And the answer is, of course not. We would not put that football field-sized data center into every single region, because you'd have a tremendously large building that would mostly be empty, and you'd be running a tiny little bit of IT gear in there, and your PUE and your CapEx spend relative to the revenue that you bring in from the services is way out of whack. So yes, there are a variety of different data center SKUs, actually, that we would specialize in markets. And by the way, the answer is not always go build a data center. Sometimes the answer to enter a market quickly or to enter a small market is we might lease some space initially or over a period of time to get started, and when we see demand grow to a certain point where it makes sense, we might decide to convert a lease into a build or a buy. And there's a team that owns this sort of data center strategy that intersects with the regional strategy, and it intersects with the capacity strategy. And so that becomes quite an interesting thing. Another thing that we work on is something called service rings, which is this notion that not every service that's available as part of the Azure platform is available in every region. But we want a predictable set of principles that customers can plan around. And so we're defining a set of service rings, and I think over time we'll be able to become more transparent about what these things are. We're sort of in the design process right now. But services would go into the service rings, and that would be based on a set of customer feedback, some dependency analysis of our own services, first parties, key customers, and then we would make sure that the services that are in like ring 0 are in every region. Services that are in ring 1 are in every geo. The services that are in ring 2 are in every developed geo. So there's a set of principles about how we approach different markets with the different services that we run. For example, I mentioned that Godzilla VM SKU size. It ends up that it's quite expensive to buy the hardware to support that VM size. We don't want to just go willy-nilly buy a tremendous amount of that hardware and throw it into every single data center. It wouldn't be cost effective. So we've got to sort of model the demand there. That's an example of a service that is not available in every single region in the world.
Yeah, one more. Your PUE was put down to like 1.2.
Yeah.
At what point in time do you see the point of diminishing returns? Do you shoot for 1?
It's a really interesting question. When does PUE go down to 1? And I guess what I would say there is we continue to find opportunities to innovate in the data center. But many of the sort of obvious places where you'd see inefficiencies, we've already addressed. So now we're looking at a variety of things that are kind of more creative. And I'll give you an example of that. Office 365 is a very interesting service because Office 365, and specifically let me talk about Exchange because that's one that I know a little bit about. Exchange does not care at all about any kind of redundancy within the scope of a region. In other words, they want 0 hardware redundancy and 0 software redundancy within a region. And instead, they want to run across 4 regions inside of a geo. And if a region fails, they simply fail over their workload. Their particular workload is amenable to this. It doesn't work for all customers, but it works for some customers and workloads. And the nice thing about that is, if you're now responsible for that service, you could contemplate running in data centers that don't need to be as highly available as the data center that's running, let's say, a production OLTP workload with a tremendous amount of hardware and software redundancy to be performance optimized and run in that one region with HA. So that's an opportunity to save costs. Now, I'm not sure that there's really a PUE comment there. Perhaps there is. Perhaps you could get a little closer to the edge in terms of cooling and have a cooling system that might be more likely to fail. So less cooling redundancy, let's say. But certainly it is an opportunity in terms of data center availability. So we sort of look at that. At the moment, we haven't encountered many customers running on public Azure who have that kind of application design. And indeed, it took Exchange and some very focused and talented people in Exchange many years to build up a model where that could work. So it's not an easy thing to do. But over time, we would love to make that sort of application model, bottle it up and make it available as something that people could reuse. And I do think that there are certainly cost savings opportunities there. On PUE, I think what I would do is I would just defer to the data center design team. No matter how much time I spend on data center, every time I look at data center, I realize how much more I don't know. It is actually really an interesting space with this electrical and mechanical building and building codes and site selection where you think about tax and power and fiber. I mean, it's really an interesting optimization problem. Yeah.
Thanks.
Okay. Thanks, everyone.